Welcome everybody to this week's episode of Ask an Astronomer. My name is Stefan. Today with me I have Eric, and we're going to answer all your questions that you have about the universe, science, astronomy. So Eric, do you want to start by introducing yourself and saying a bit what you're working on?
Yeah, sure. So thanks, Stefan. Good to be here. Like you said, my name is Eric. I'm also a PhD student at the Institute of Astronomy in Cambridge. Like Stefan, I'm a cosmologist. Oh, thank you for the slide. So I mostly study the cosmic microwave background, the CMB, which Stefan has helpfully put up for us here. And yeah, that's just this old light from the early universe that I can talk a bit about later, I think, if people want to ask about it.
Then there was the keyword to send in questions.
Yeah.
Everything about the early universe.
We use that to study, I don't know, the composition of the universe, the evolution of the universe, inflation, neutrinos, all the fun stuff.
Okay. So let's start maybe by a question we just received beforehand on Reddit, which was about neutrinos. So imagine tomorrow someone invented a neutrino telescope, so something that could detect neutrinos very easily. What would you first point it at? And while you answer those questions, thanks for the note in the YouTube chat. I will go and fix the Slido. 1 second. Go ahead.
Oh, you want me to take it? Okay. So neutrinos. Well, like I said, my main study is the cosmic microwave background, and that is this background radiation we see in light in microwaves. There's also an analogous thing that is expected called the cosmic neutrino background. It would have been emitted somewhat earlier than the microwave one, and that's background radiation in neutrinos. It hasn't yet been observed because neutrinos, as you may know, interact very, very weakly. They're these extremely weakly interacting particles. So I'm not sure exactly what we would learn by observing the CNB, as you call it, but that's kind of part of science, right? Is you learn more things as you observe new things. So I think that would be really exciting. Another thing that is related to my own research experience is that I used to work on a dark matter direct detection experiment where they're trying to detect these things called WIMPs, weakly interacting massive particles. And that's actually been in the news recently with the Xenon 1 ton that some people may have heard of, but I'm not going to go into detail on that. Anyway, the point is that those are soon going to get to a sensitivity limit where if the dark matter interacts less weakly than a certain level, or less strongly than a certain level, then you'll start seeing solar neutrinos, so neutrinos from the sun instead of dark matter, and you won't be able to discover the dark matter. So if you have this fancy neutrino telescope that our Reddit friend is suggesting, then you might be able to get around that neutrino background and keep looking for dark matter. Do you want to say a few words about astrophysical stuff?
Yeah, I mean, of course, we are pretty biased here that we have two cosmologists here, so of course we want to point it at the background. But there are like tons of astrophysical examples where I would really like to see the neutrinos coming out. For example, supernovae, or in general very massive and energetic things. There are often very high densities of material, so that photons have a really hard time to get out. So, for example, in the supernova, I think photons take quite a while to get out of the kind of center of the supernova to escape, while neutrinos can escape much faster. So you could, for example, use this neutrino telescope to search for supernovae before you actually can see them with light, then point your normal telescope at them and kind of get a really nice light curve from before to after. I'm not sure how much the delay actually is, but I think that would be really cool. And you could do things like test if the speed of neutrinos is the same as the speed of light, and all kinds of really amazing science, I suppose. Okay, so yeah, right, for the Slido link, so in general, I should explain this for people who haven't been here before. You can just ask your questions anywhere in the chat, so on Periscope, on Twitch, YouTube, or in the Slido link. That is, that Slido link is, so you go to sli.do and you enter the number 67628. not to 7, that number's outdated. I'll update it next time. That had expired. Okay, so much for that. And back to science. We got one question about fast radio bursts. Have you already heard of them, Eric?
Have I heard of them? A little bit.
Yeah, my supervisor is actually working a bit on fast radio bursts. So I'm not an expert in them myself. So maybe I should explain a bit what those are. So when we look in the sky with radio telescopes, and especially with ones that have a really wide field of view, so they look at a really broad part of the sky, we sometimes see really short kind of flashes of radio energy. That's what we call fast radio bursts. Fast because they're really fast, and usually they only happen once at a certain point, and then we don't see them again, and we're not really sure what's causing them. But there's some that repeat. So there's like at one point in the sky, like in the regular intervals, we get the signal. I think there are 1 or 2 sources we found until now that kind of repeat, and they're like lots of
more.
More? Okay, there were 1 or 2.
It's not very many, regardless.
Very few, let's say that. And yeah, you can use them for like most things that they would use to kind of map. So if you think, okay, those come probably from some very kind of high energy phenomenon, like galactic centers or some kind of explosion, then they usually come from a region of the universe where there is lots of stuff in general, so lots of matter. And yeah, if you see where all these fast radio bursts come from, you could use them to map out where the matter is in the universe. And because they're so bright, you could use them to look very far at very far distances. And the source of them are not completely known, I'm sure. I think there are like lots of theories, and I think magnetars, so this is just quasars, so neutron stars, I think. Magnetars and neutron stars, right? That spin very quickly and emit various kinds of radiation, and they're called magnetars because they have strong magnetic field. And I think they're one possible source for FRBs. I'm not sure if it's confirmed already. I don't think it is confirmed.
So there's this radio telescope called CHIME in Canada that I think has just started observing recently-ish, and they're meant to discover loads and loads of FRBs, including repeating ones. So that should really teach us a lot more in the next few years.
Yeah, that should. Eric, do you know something about if the CMB has max entropy, and if so, does it violate the second law of thermodynamics as the universe evolves?
So I'm not totally sure what that means if the CMB has maximum entropy.
I mean, certainly it has some kind of order in the information, so it doesn't like. I mean, it's not like a uniform soup of stuff. It's not like white noise or anything. So it's not like kind of an extremum, I would say. And so what it
I mean, you can say in the sense that it is black body radiation, right? So that is like the maximum entropy.
Yeah, well, okay, so every
constant temperature thing.
Yeah, that's true. So kind of every individual pixel, kind of like the if you look at the parts of the CMB, the spectrum will be a black body spectrum. So this is a very generic spectrum that essentially everything that is somehow warm emits. So that will have not much entropy. But if you look
regular thermal radiation. Sorry for the jargon.
Oh yes, right. But if you look at any particular point, they can have different temperatures. So even though the spectrum is really boring, the temperature distribution, so you see all those white and orange spots, are very different. And in general, like the universe does conserve, I think it's a Comoving entropy, so density. So entropy is a term that is related to kind of, you could imagine it how ordered or how unordered the universe is, or material in general. And the kind of, well, how do I explain Comoving? The entropy density, and taking into account the expansion of the universe, is a quantity that's conserved, that's like a bit related to thermodynamics laws.
I mean, really, you could just say that as the universe is expanding, the cosmic microwave background photons are also expanding. So the CMB temperature cools, right? And that cooling is the same thing, basically, as entropy conservation, or co-moving entropy conservation.
Okay, yeah, that sounds reasonable. We got our question on YouTube again. Is a big crunch still a theoretical possibility? Eric, do you want to say this? I heard.
I think we have differing opinions on this. I mean, I'm not going to say it's not in the current accepted cosmological model that we think is true based on cosmic microwave background measurements and other measurements, but it's still not completely set in stone. But the current standard says that there will not be a big crunch.
Maybe we should explain what a big crunch is. I forgot to do that.
Yes, the big crunch is the idea that, you know, the universe starts out with a big bang, it expands, and then it slows down, and then collapses again. So the universe ends in a big crunch with everything collapsing together. So current observations show that the expansion of the universe is not just expanding, but also accelerating. So it's speeding up as everything's moving away from everything else, and that's due to dark energy. That's just the name that we give to the mysterious acceleration, right? And so yeah, if that cosmic acceleration continues, which we think it should, then you're not going to get any crunch.
Yeah.
But it is a mystery, so who knows?
Yeah. Okay. So it doesn't look good for the big crunch, but well, maybe you can come up with some surprises for us in the future, dear universe. We got actually a kind of related question, which is why did galaxies stop forming? And I think that's a quite interesting question. So most of the galaxies formed kind of early on in the universe when there was still a lot of matter and it was, well, somewhat more or less kind of distributed everywhere. And then it started collapsing into clumps of matter which formed the galaxies. But as the universe expands more and more, this matter gets apart more and more. So like if the universe wouldn't be expanding, nearby galaxies or nearby kind of big amounts of matter could fly together and merge and form bigger and bigger galaxies. But now that everything is expanding, objects that are far away from us are getting pulled away by the expansion of the universe. So they can't kind of fall into us anymore, merge with us, or form new bigger galaxies. So actually the only major galaxy that's going to fall into the Milky Way in the future at all is the Andromeda galaxy, which is on a collision course with us. But all the other big galaxies are moving away from us because of the expansion of the universe. So that's kind of the reason why, well, one of the reasons why the kind of clumping and forming of galaxies has stopped. We got another question on Slido. What did people think of when they discovered the other planets? Do you mean the solar system planets, or do you mean actually exoplanets? I'm not sure what people thought of planets. I mean, yeah, I would have to check some historical books. I suppose that they might have like thought that. Well, I think like when the planets were discovered, so this was like I think Galileo's time. I think. Well,
the planets were definitely discovered in antiquity, right?
Okay, well, they found them. Yeah, that's true.
Not all of them.
I'm not sure if they figured out if they also are different from the stars, though. In the antiquity. Well, anyway, when they discovered the planets, they had a clear idea of the solar system and what the sun is and what the universe is. So back in the days, I'm not sure how well they kind of understood the whole picture and realized, okay, these are planets, these are stars, this is the sun. We are circling around the sun. I think this took them a few years to figure out. So yeah, I'm not sure what they thought when they did that. How did the idea of aliens living on other planets evolve? And do you want to do that, Eric, or should I?
I mean, we're not historians of science, but I mean, yeah, why don't you give it a go, and
I mean, we're kind of. Well, we're not really historians. I recently heard a talk where someone compared cosmology with, what was it? I think paleontology, because we kind of look at or archaeology, because we look at like kind of the remains of the universe or all the old stuff that we can see and try to infer what happened back then.
Oh, absolutely, and that's part of why I love it. But that's different from history of science.
That is indeed true. I have to admit. Okay, so I'm not an expert in history. That's true. Anyway, ideas of planets. So I would assume that people figured out, okay, we have the sun. Like, I mean, eventually people figured out the solar system. There's a sun. We are a planet around the sun. And when you figure out, okay, there are other planets that are also flying around the sun, the conclusion that there might be life on them as well isn't that far off. And at some point we found out, okay, maybe there's not life on the other planets in our solar system, but we found out, oh, there are billions of stars, so billions of other suns in the galaxy, and there are even more galaxies. So there are lots of planets. I think that's kind of one of the main, at least for contemporary people, one of the main motivations to think that there is probably life out there, because there are just so many planets that you have like lots of chances for life to evolve.
I mean, I would expect that as soon as people figured out that there's something beyond the Earth, then there was speculation, well, could there be life beyond the Earth as well?
Oh, so we got a lot of questions in the YouTube chat, and I see a lot of planet names. I'm not really an expert on planets, but I'll see what we can do.
We'll do our best.
Why do we still see gas and why do we see gas and dust in spiral galaxies and not in elliptical galaxies? So the shapes of galaxies kind of evolve with time. So I think most early galaxies are mostly kind of spiral shape. The precise reasons I can't confidently tell you about, because it's not at all my area. But the general evolution is from something like spiral type to something elliptical. So the older the galaxy gets, well, elliptical galaxies are typically old galaxies, and spiral ones are, well, newer ones. And many processes, so for example, if you have a supernova exploding in a galaxy, or like other big explosions, they will kind of, I'm not sure if they actually blow out gas out of the galaxy, I don't think so. But certainly stars forming use up some gas. So they will have to burn some gas. And if you have, for a star, you need a very dense cloud of gas, and if you burn through that, and afterwards you have a supernova explosion, that gas is kind of distributed away, and it's not easy to. Yeah, I'm not sure if that's actually the reason why we don't see the gas. But certainly, like I know that star formation is kind of stops in old galaxies compared to new galaxies. So there must be kind of more gas that can form stars in new galaxies. That's certainly something you should see. I'm not sure about gas at all, like in total.
Yeah, either. As far as dust, I think all the ellipticals do have quite a lot of dust, actually.
Okay, we got a question about, is gravity directly proportional to explosion? I'm not sure what you're referring to in that case. But you asked about gravitational lensing, so we had one question about gravitational lensing. Do you want to say a bit about what this is? Kind of in general.
Sure, I love gravitational lensing, especially weak lensing.
Well, I can give you strong lensing
slide. I guess that's kind of hard. Okay. So gravitational lensing is, let's see, where to begin. So light gets bent by gravity, or the path of light is affected by gravity, just like the path of any regular object is affected. So you can think of light going by a massive galaxy or a massive cluster of galaxies, kind of starts falling in towards that galaxy and then gets its arc bent. And so that can distort images of faraway galaxies that are behind massive foreground objects. So in Stefan's image here, we have this blue ring is a single galaxy, I believe, that the light has been bent in all sorts of ways by this gravitational lens, this foreground thing, into a lovely ring. So that's what we would call strong lensing. There's also weak lensing, where instead of having one really big massive thing in the front, you kind of have more diffuse, maybe, foreground matter that is going to distort the shapes of background galaxies and background images in more subtle ways, but coherent ways that can be measured. So if you have a big field of galaxy images, say, then they'll all be distorted in a coherent way that you could, in principle, back out from the images and then learn something about that matter distribution. And this is something that a lot of people are trying to do, to learn about, you can get a lot of cosmology out of it in general. I was going to be more precise, but it's very broad.
Yeah,
it's a difficult thing to do, but it's really exciting. And there's also gravitational lensing of the CMB, which is the same idea.
I mean, that's like the ultimate thing. You have the CMB, and then you have lensing. That's great. Well, I mean, I think it's not that like practical in cosmology, but I think the idea is really great to have a CMB and then it's lensed. Anyway, we got
I mean, CMB lensing is measured.
Yeah, sure.
And the upcoming experiments are really focusing on trying to do it. I work on some of those experiments.
Okay, I have no idea about this topic. I should let the expert talk about this.
Don't diminish CMB lensing, Stefan.
Sorry. We got a question for a book in the beginning, actually. Someone asked about, I think, a kind of a children's book for astronomy. A few friends of mine recommended George's Secret Key to the Universe, which is by Lucy and Stephen Hawking. And I think it's just 3 books, and they're supposed to be very good. So 2 of our other students recommended them. So I can just forward this recommendation. I think it sounds good. On Periscope, we got a question. If we, in dark matter, well, in filaments, so the kind of matter that connects the big clusters of matter, if we expect the same proportion of dark matter to baryons as in the normal matter, like everywhere else in the universe. Do you want to say something about this, Eric?
Sorry, I was looking at the book recommendation. What was the question?
Do you expect proportional dark matter? So yeah, do you expect like the ratio of dark matter to normal matter to be the same everywhere? In particular, in these kind of filaments that connect the big clusters. So I mean, I suppose I should first say what are filaments, before I let you talk about this. So when you look at the universe on a really large scale, so let's imagine you take a picture of the universe, and then you zoom out and zoom out and zoom out, and you take kind of a really broad view. What you see here on this picture on the right is actually a simulation, because we can't really do these pictures in the real space, and so we rely on simulation. But we are quite sure that this is quite close to how the universe actually looks like. And this is well, 500 million parsec, which is about 1 billion and a bit light years. And so this is a really, really large kind of scale. And you can imagine kind of galaxies are somewhere like along these filaments that are connected to big clumps, or in these big clumps. So there's most of the matter, and in between you get big voids where there's almost nothing. And the question is now kind of, is in these voids where there's almost nothing, or in these filaments in between everything, or in these clusters, is there the same amount of matter, the normal visible matter versus dark matter, as everywhere else? I mean, so
I don't know.
If you go to very small scales, I suppose you will find a big difference. I mean, obviously, okay, if you look at Earth, there's, well, 1 planet worth of Earth of normal matter on Earth, and there's about I think it was 1 ladybug worth of dark matter on the planet. So the dark matter that's kind of in the volume of Earth is really low, because the dark matter is much more smoothly distributed. So like the whole solar system is really like washed out in dark matter. It doesn't like clump in planets very strongly. And if you go on larger scales, it actually it's less dramatic, this effect. So I think if you would look on these really large scales, it should be almost the same, because the dark matter does have effect, like there are supernova explosions and other big explosions that cause the matter to move around. But I think they're not that strong that they could disrupt, like, to make a big difference on scales as large as these. We got 1 question that's too long for our window. I'll work on this in a second. Meanwhile, we should go back to some of the YouTube question. And oh, there are lots of questions. So it's so we are this. Yeah, right. The question regarding planets was the planets on our own solar system. So we discussed this a bit. I mean, we are not very experts in history, so that's not our main expertise. Why did Saturn tilt on axis? I'm not exactly sure what's the precise reason why the axis of Saturn is like tilted compared to its rotation. So usually you would expect, if you have a big cloud of, so that's actually a really nice idea. So if you have a big cloud of gas and it kind of falls together and forms a star, and why does it always form a disk around the star? So maybe how do I do this? So if you have a star here, so you have a big cloud of matter, it falls together and forms a star. And usually what happens is you get a disk around the star. Let me just show you a picture for this. I'm sure I have a picture of a disk somewhere. Here. This is a so-called protoplanetary disk. So when you have a star and the matter falls in and falls together, you get a disk. And the reason for that is you have some angular momentum in the gas cloud. So you can imagine if you have something that's spinning and you try to move it around, like stuff usually keeps spinning. Like if something is rotating, it wants to keep doing that. If you have a chair that's rotating, it wants to keep doing that. And even if you like compress this down, it has to keep rotating, so it can't get compressed down to kind of a point. It has to be something that's it has to be like some size, some minimum size or rotation speed. I mean, it has to conserve the angular momentum. If you add everything up, there will be one direction of spin left over, and this is why you get a disk, which has like, it's all spinning in one direction. And this is why you would expect all the planets that also form from kind of their own disks. Do they? I think, I'm not sure if they form from their own disks. Anyway, they form from the stuff that's in the disk, which is all spinning in the same direction. Yeah. So you would expect let's say the rings of Saturn to also spin in the same direction. And there are some like effects of, I'm not sure what exactly it is, like if it's collisions with moons or other objects, or what exactly caused the moons of the rings of Saturn to be misaligned. So I think I asked this when next time we get an expert on solar system, I'll forward them the solar system questions.
Yeah, sorry.
That's fine. That's fine. Okay. So we got a question how to become an astronomer. So I mean we can't like, please, if we are students, right? We are PhD students. So we're not really like the best persons to kind of ask for like career advice and advise what you should study, or what you like, should choose to what subject you need to study certain things. In general, like if you're interested in math and physics, these are kind of the main things that you will need for astronomy. Like depending on what you do, you will need to do like lots of mathematics, lots of calculations, or usually like these days you will also need to do a lot of programming. That's kind of a thing that's involved, and of course physics for basically everything. So I suppose that's a good start. Like if you are like you say you're I think you're 12 years. So right, was it 12? I think it was 12. So you don't have to worry about specializing in astrophysics now. It's fine if you just can just keep your interest in science and physics and math. Do what you think is fun. And I mean you can do things like learn about stars when they interest you. You can go out. There might be astronomical societies that where you can go if you want to learn more about the kind of everyday sky. Although that's not something I do very much except for Monday evenings here. So but it's still very interesting. I'm rambling about things I have no idea of. Let's go back to some physics thing. Why is the temperature of a black hole inversely proportionate to its size? Do you want to answer this, Eric, or should I do the black hole question? I thought that you have a question about limitations of the Big Bang theory. Okay, so let me talk about black holes for a second. Right, so with black holes, there's a certain phenomenon. So maybe, did I talk about black holes today yet? Not yet, right? So black holes are really compact objects. Black holes are objects that are so dense that light can't escape from them. So Eric just discussed lensing a bit ago. And what happens if you have a really massive object is that the path of the light gets curved. And if it gets curved too strongly, it can kind of fall into the black hole. Well, then it is a black hole, and it doesn't get out again because the gravitation is kind of too strong. I mean, it's more complicated, but that's kind of my simplified explanation. And right, what can happen is if you have, well, it's of course also more complicated. I'm massively simplifying, But imagine you have this black hole which has an event horizon. This event horizon is kind of the point from which nothing can escape, right? So that's kind of, well, it's not exactly the black thing you see, but it's more or less this black sphere that you see around the black hole. And if you have particles that created, so if you have a vacuum and you have light, or in general, from a vacuum, from the uncertainty principle, you can kind of borrow energy from the universe and create particles and then have them annihilate again. So this is kind of a process that happens all the time in the universe. But what's special is if it happens close to a black hole, because what can happen, or that's how you can imagine it, how I imagine it always, is when you have one particle falling into the black hole and the other is kind of, well, left and flies away, and it doesn't have its partner anymore to annihilate. So it's just a particle that's created, and it's radiation that comes out of a black hole. So every black hole kind of emits some energy in this form. And this energy, so it's like energy that a black hole loses, so we say evaporates, and this is this radiation. And the question said, why is this proportional to, I think, 1 over the mass? Oh, Eric, you got a question on YouTube. Right. The reason for this is the radius of a black hole is proportional to its mass. So if you have a black hole that's double the size, it will have 4 times the radius. And I think the okay, what exactly is the Hawking radiation proportional to? I'm not an expert on this. I would suspect that just because a black hole surface is much smaller, if you have a smaller black hole, that's why it seems to be brighter. But I think the amount of mass that you're evaporating from a big black hole should not be smaller than from a small black hole. It's just that the surface is much bigger, so it's distributed over much more area, which would explain why it would be not so bright. I think actually YouTube questions didn't work for me on my phone, so if you saw more YouTube questions, Eric, you have a question for you. Do you want to answer a question about fruits?
Oh, I thought I was going to get to answer the Big Bang one, but
oh yeah, right. Never mind. Go ahead with the Big Bang question first. It's actually a science question.
Okay. Yeah. So the question is, what are some of the limitations of the Big Bang theory, and are there any things which it cannot explain? So I think that's a really interesting question. There's kind of a difference you can make between, well, first of all, you have to specify what exactly you mean by the Big Bang theory, and I'll come on to that. But there's a difference you can make between, the Big Bang theory is not going to be complete. So there are some things that it doesn't try to explain. And then you can also see if there are things that it should explain that it fails to achieve. So I will, in the latter category, briefly try to explain something that we call the horizon problem. So maybe you can help me out on this, Stefan, but I'll give it a go. So if you look at, for example, my favorite, the cosmic microwave background, then you see correlations, so things that have the same temperature or are related in temperature on parts of the sky that are very far apart. And so if you take kind of standard general relativity and run the universe backwards, which we can do, then you're going to see that these things, these parts of the sky that are far apart now, should not have been in contact at the beginning of the universe in what we call the standard Big Bang theory. So then that creates a problem, because you need a reason, or you would like a reason that these things should be correlated.
I think what you could imagine, like as an example, imagine you have like some kind of Earth that's expanding. It's weird, but don't like it's weird. Okay, but imagine you have like a planet. It's expanding all the time, so the surface is getting bigger, and you have different people living on these different points, right? And then you're an alien. You come to visit this planet, and you find out, oh, the people are all the same size, like more or less. They're all like 1.80 meters-ish. And then you think, okay, how can they be all the same size? If they have, so you find out, oh, if you run this plan backward in time, if we look how it would have looked like in the past, we find out, oh, those people could have never been in contact. There was always, say, water between them, or like the planet was expanding too fast. They could have not the one person from the one continent could not have gone over to the other continent. And then we'd say, okay, why are they still the same size? I mean, with evolution, there's some ways to do this. But in the case of the cosmic microwave background, this is a legitimate question, right? You think, okay, why is this point on the sky and this point on the sky exactly the same temperature if they had not time to kind of send a photon from one to each other to kind of send energy between each other to make them the same temperature? So that's kind of the
Thanks for the analogy.
The analogy. There you go. Go ahead.
Yeah, so the solution that is currently the most accepted one to this problem is something called inflation, and that's basically just a very early period of extremely rapid expansion that, I mean, since it is an early period of fast expansion, it does fit into kind of what we colloquially think of as the Big Bang, but it's not scientifically what the standard Big Bang theory was. And I'll note that inflation also serves a important role these days that a lot of people take even more seriously than this horizon problem that I described before in seeding cosmological perturbations. So it's a way for us to explain where the initial heavier spots and lighter spots, or hotter spots and colder spots, come from, that will eventually grow into clusters of galaxies and planets. And that can be explained in that inflationary theory.
Okay. Yeah, we also got a quite long Twitch question about inflation, which is basically, I think, more or less answered by your question. So there's one question in the one part of the Twitch question is whether, like, so you say this inflation kind of gives you the perturbations, the initial differences between different points. Could it be that there's a place where inflation is still ongoing? Like that maybe there was, by random accident, a place where there was more of whatever caused inflation and it's still going on? Or did inflation stop everywhere already?
Yeah, I mean, so you can imagine that there's a region where inflation would still be ongoing, and it's just outside of our zone. I think there's issues with this.
Yeah, I suppose it must be really, really far away from us, because otherwise, like okay, so inflation is really, 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 really fast. So like this figure doesn't even nearly give credit to it, right? So you have a really, really, really tiny fraction of a second, and the universe expands by, what is it? Like a number with like 20 zeros or something? Like it's a huge amount. So inflation is incredibly fast. And if it would be somewhere, inflation would be ongoing until today, this part of the universe would expand so massively, like unimaginably a huge amount. I can't do the numbers in my head, but it would be enormous. And it would be really hard to like have this going on and us not noticing. So of course you could say it's like somewhere really, really far away. But I suppose this might reach some philosophical problems eventually. We got two questions that are kind of relating the ideas of time and space. So let me start with the one question. Is it true that the galaxy we are able to see right now is just the light of the galaxy that has reached us maybe years later, since light takes the time to reach us? So that's exactly the case of, like, light has a finite speed. Light travels by 300,000 kilometers per second. So this is really, really fast. But if you look at the really, really long distance to our sun, it takes about 8 minutes for the light to get from the surface of the sun to us. And if you think about distances to other stars, it's even further. So the nearest star is, I think, Proxima Centauri, and it's a few light years away, which means a light year is a distance light travels in 1 year. So this nearest star to us, except for the sun, is so far away that light takes 4 years to travel to us. And the furthest part of the galaxy is hundreds of thousands of light years away. So light takes 100,000 years or so to get from there to us. So the stars the light that we see is indeed that old. And the stars that we see are also that old. And this gets even crazier when you go further and further away. So if you look at the Andromeda galaxy, the light will be a million years. About a million years old. Maybe 2 million. And if you look at things that are further and further away, it will get older and older. And if you look at the cosmic microwave background, so you can actually see the Big Bang. So what you see there is actually that light that is on the ray since, well, not the, sorry, I shouldn't say they see the Big Bang. You can see the, well, the kind of hot stuff that the Big Bang left behind. So you see whatever there was 380,000 years after the Big Bang, but the light has been away on its way to us for basically the whole lifetime of the universe, like 13.8.
About 13 billion years, yeah.
Yeah.
13, 14, somewhere around there.
Yeah. So it has been around, yeah, so that's exactly what happens. Like light is quite slow actually, and we would really like to go faster than light, but at the moment, well, light only goes that fast and we can't see further than that. Which is also really cool, which allows us to kind of see all times of the universe, right? I mean, if light would be really fast, we would just see today everywhere. But light is kind of so slow that we can just take our telescope, look somewhere, and see how was the universe 13 billion years ago. I think that's amazing. And there was another question, if you can explain the space-time relationship a bit more. So what's space-time and how does it, well, affect not necessarily our everyday life, but yeah.
And it's been so long since I did relativity. Yeah, I think the basic idea of space-time is that
we'd have a nice
you have this. I don't know.
Okay,
I like to start with the experimental fact that basically you can't catch up to light. So no matter how fast you're going, you're always going to see light moving at the same speed. And that is kind of the basis of special relativity, and you do a lot of math from that. and end up finding out that you kind of have to treat, or the best way to do it is to treat time and space as kind of part of the same thing. Help me out, Stefan.
Yeah, I'll try to come up with some analogy.
He's good with the analogies.
Yeah, right. So as people figured out, like if you treat, as you just said, time and space separately, it doesn't work out. And actually, they are somewhat together. And yeah, when you so let's start with talking about objects. So if you have an object like the sun or the Earth, they do bend space-time, is what we say. And what that means is that they cause space, well, to kind of change its length and how fast time runs around them. So let's say you're close to a big massive object like a black hole. Like, for example, in the movie Interstellar, which is actually a really nice demonstration of many physics effects, your time will run slower for you as long as you're close to a big object. So if you're on Earth versus if you're floating somewhere on space, while you're on Earth, time will run slower. So you could say it's kind of a time machine into the future. If you're close to a black hole or something other that's really massive, time will run much, much slower. So yeah, I should say this about Earth. The time difference is really, really tiny, and like there's no way you will notice this ever. But if you go to a black hole or something, it can be a huge time difference. Like the time outside of away from the black hole can run 100 times faster or 1,000 times faster, depending how close you get, than the time close to a black hole. So that's a huge difference. And the other thing about this space-time stretchiness, so there's an analogy people always use is when you think about a rubber mat and you place a heavy object on it, you get this kind of curvature. And this is a bit how you can imagine that objects like the sun change space-time. And if other things like planets or light go along this curved path, they also get curved. So that's why a planet goes in a like an elliptical orbit around the sun. It's not, well, it's because the sun attracts them. But the reason for this attraction is actually the deformation of space-time. So this bump in space-time, which kind of makes all the gravity happen, which is kind of the idea behind relativity. I think we got
Can I use that to talk about space travel for 2
minutes?
minutes?
Oh yes, do that, please.
I love talking about this. So basically, space is very, very big, and therefore you can't. Well, okay. Assuming we're limited by light speed and you don't have like wormholes or some weird warp drive or something, which would be cool but currently thought to be impossible, then we sadly can't have Star Wars or Star Trek or anything like that because, like Stefan said earlier, the closest stars are a few light years away. Go farther, then it can be hundreds of light years. But the fun thing about relativity is if you get in your spaceship and you have a super fancy spaceship that goes really close to the speed of light, then from your perspective, being in the spaceship, you can get 100 light years really quick. So you would be fine, you wouldn't age, it would be chill. You would get there. And then it would all be one-way trips because the latest information you have about your destination is 100 years old if you're going 100 light years. And if you want to send a message to your friends at home, it's going to take 100 years to get there. And you've already been 100 years away from their perspective. And two-way communication doesn't work because space is too big, no matter how fast you go. So it's a little depressing, but I think it's cool also.
I mean, maybe eventually we will figure out how to get around this stupid, annoying light speed limit.
I don't believe it, but maybe.
I'm sure we will eventually find out something. Like, you know, people always have been very confident that the universe is the way they think it is, and it never turned out to be right. So I somehow hope we are not right this time, and I'm sure we'll find more exciting stuff. I mean, there's still mysteries in the universe, like dark energy. We don't know what dark matter is. I mean, there's like, as long as the stuff we don't understand, I'm not confident that we have found the solution for everything.
You're an optimist. I like it.
Ah, yes. So we got a technical question on Periscope. Sorry, I have no idea what the scattering phase function is. So I suppose you have to check whatever some papers from astronomers. I'm not using scattering phase functions in my day-to-day business, so I sadly can't talk about this. Yeah, so regarding the question, we got another on YouTube regarding the astronomy question, what course you should take. Sorry, I can't, I have no idea what courses you have to take in your country. Like, I come from Germany, I kind of know what's there, but I really have not that much information about the UK or any other country for that matter. I would suggest...
Are we talking about high school courses?
I'm not sure if it was high school or university now. Well, anyway, I suppose just the best point to ask would be like the local person at your university, or people who do astronomy in your country, because they will know kind of the system. Oh, Eric, you got a follow up.
High school, I would just take as much math and physics as you can.
Okay. There's a follow-up question for you, Eric. What is the fastest spacecraft?
I don't know anything about spacecraft.
You just talked about spacecraft. Well, space travel.
I was talking about hypothetical spacecraft, not real spacecraft.
Okay, so what's the fastest hypothetical spacecraft? I suppose speed of light, right?
Yeah.
Okay, well, that's boring. Real spacecraft. Okay, so how fast is the Voyager? I think the New Horizons probe that we sent to Pluto was one of... Okay, so I'm not an expert on like actual space travel. I think the fastest things we have sent until now were kind of the probes that we sent out in the far universe. Well, not universe, like far out in the solar system. And I think for quite a long time, the Voyager probes were the fastest objects that we made, like the fastest spacecraft that we made. I think one of the newer ones, I think like the New Horizons probe maybe, that went to Pluto, was faster. But I'm not exactly sure which one of those is the fastest. Actually, what's interesting is the way you get them so fast. So rockets, like rocket fuel, and like, you know, this doesn't really bring you up to speed. So the way you get to really high speeds is taking the assist of big planets in our solar system to kind of steal a little bit of speed from them to speed yourself up. So that's what the Voyager probes did, what most of the probes do that we send out in outer space. We just give them enough fuel to kind of get away from the Earth, and then we let them fly by, like Mars and Jupiter and Saturn, and every time they fly by those planets, they steal a little bit of their energy. The planets won't notice, no worry. But those spacecraft will gain a huge amount of kind of speed, and that's what allowed Voyager, like, I mean, when did we build Voyager? Like, years ago, like, it's really long.
Oh, ages ago.
Yeah, and it's still, like really, really fast. So that's how you get fast spacecraft.
And this is why they have very narrow launch windows, and for these kind of things, you have to make those precise maneuvers around all the planets.
I'm really super impressed by like people who make spaceflight, like spacecraft. Like they have to plan where is with what planet, and then figure out, a way to make the spacecraft go by this planet and then by this planet and then this planet, it's amazing. I don't have any book recommendations on this though. Didn't read any books recently on space travel. Okay, so I think I might have skipped a few of the YouTube questions. What do we have? Oh, what are Uranus and Neptune made out of? So planets. Oh, and I'm not sure if gas giants actually have central cores. So I think they don't. Like it's kind of a gradual transition. So at the outside is like really thin gas, and the further in they get, the further like the more dense it gets. But I don't think they have actually solid cores. I think in one of the past episodes, one of our solar system people explained this with competence. So I'm more like a cosmology person that can tell you about the universe, not about the solar system. But yeah, they're made out of gas, so mostly hydrogen and helium. Because actually, yeah, I think it's mostly hydrogen and helium, right? For gas giants, I suppose, because that's like what most stuff at
Jupiter and Saturn, I think is different for the ice giants.
Oh, okay. Okay, so then I'm actually not even sure what they're made of. But it's gas, and I think it's gas all the way down. Like it gets denser and denser, but I don't think it gets solid, actually.
I think the gas giants have some kind of non-gas core.
Okay, let's. I will ask the next planet person. I see.
Yeah, apologies, we're not planet people.
Oh, there's a question for the CMB field here. Do you expect a change in CMB due to parallax effect, likely to in a parsec range? Right. So when what do you mean? It's we move around through the universe, and then we might see a different CMB. So I think the effect is really tiny. Eric, did you look at this in detail before?
So there was a paper about this the other week.
Okay.
I can say, so the parallax, if people don't know, is the usual parallax is when the sun is going around what am I saying? When the Earth is going around the sun, then you're on opposite sides of the sun at 6-month intervals in orbit. And so you can use that distance to, I'll back up a little bit. When you're on those different sides, then the apparent positions of things like nearby stars will change relative to really far away things.
Let me make an analogy again. When you stand in your garden and look at the next... Oh, okay, I can't do the eye demonstration. Well, actually, you can do it. Like if you hold one eye closed and look at some object like this webcam, and then you switch to the other eye, it kind of shifts slightly. And you get a similar effect by, let's say you look at the sun tower outside, and then you go a kilometer in one direction and look again in the same direction. So let's say you look in the north direction, the tower will have shifted a bit. And you can do the same in space with like stars. It's just that all the distances are much larger. So you just wait until the Earth went once around the sun, like halfway around the sun, and then look at the sky again and see how the positions of objects shift. Yeah, sorry, I interrupted you. You want to say about
No, it's fine. It's fine. So then that's the normal one that is used to measure distances to relatively nearby things like stars in our galaxy. And then there was this paper suggesting that you could use some other kind of parallax, which was like the movement of our galaxy in space, which our galaxy moves quite quickly through space. Or maybe it was the Earth in the galaxy. I don't know. It was some larger scale movement. This was a few weeks ago, I'm sorry.
Okay. And
I think they thought that it could, in principle, be detectable. If you give me 2 minutes, I can look at the paper.
Okay. We might come back to this. We got 2 new questions. Does time exist only till we don't reach thermodynamics equilibrium? And that's kind of a question that goes into what is time actually and how can we notice time runs. So actually, one interesting thing about physics in general is almost everything runs the same if you just kind of run the clock backwards. You don't have only have to run the clock backwards, but say you kind of mirror everything, you would change the charge of everything, and you let the clock run backwards, then almost all of physics looks the same. Like all the I think all the particle physics and like fundamental elementary particles behave exactly the same if you do these two things and let the clock run backwards. So if you look at a reaction, you wouldn't be able to tell what way time is going, like a particle physics reaction. But there's one thing which we call entropy. And the idea is that, there are like a few caveats, so it's like in closed system, etc. The entropy, so this kind of, well, I said before, kind of the order of stuff, so how ordered something is always increasing. It's how unordered something is. So stuff is always getting less and less orderly and more mixed up. I mean, just imagine you have a bunch of hot water and a bunch of cold water, and you let them two in the same bottle, then they will mix, and it will get more and more mixed up with time. And that's a process you can use to see, time is running in that direction. Because if you have a bottle of, well, medium warm water, it won't suddenly, unmix into hot and cold water. That doesn't happen. So the question is kind of, okay, what if everything stays the same? Like if stuff stops mixing, if we have everything mixed up, does time stop then? And I suppose time in the classical way of time, things are happening on time scales, like it would be still running, but there would be nothing changing in the universe. Like if the universe would be completely homogeneous, everything mixed, everything's the same, then there would be no way for you to tell if time is running at all, what direction time is going in, and there wouldn't be any humans anyway. So you would also be not there to measure it. But I suppose you could say well, maybe you can't. It's hard to define time in that place. Yeah. Eric, did you figure out something about the CNV already? Sorry, not the CNV. The parallax.
I did. So this is tangential to the original question, but I'm going to go with it because this is what this paper is about, and it's what I was thinking of. So the idea is it's not actually parallax with respect to the CMB, but it's okay. It's wait. Let me turn off the phone. Hold on. It's with respect to the CMB frame. Anyway, the point is the Earth is moving very quickly with respect to this reference frame defined by the cosmic microwave background.
So
as it moves, you get this parallax effect where in different positions, it's actually going to be the apparent motion of all the galaxies or the apparent position of all the galaxies is going to shift towards I think it's the opposite direction of the way you're going, but it's some direction. That's what's important. Yeah. They're all going to shift coherently to some direction. And the hope is that this could be measured with some next generation galaxy survey, like LSST, now renamed the Vera Rubin Observatory.
Okay, so it's still futuristic, but you might be able to see effects of the Earth moving through space.
Probably. And naturally, they want to use that to measure H0.
Of course. Let's discuss that another time, probably, because we're almost at the end, and we have at least one question remaining. Right. So the CMB might be harder to measure because it's just much farther away, and as everything the further something away is, the harder it is to measure the kind of change due to our movement, because it just doesn't matter that much. Is it possible that there are multiple black holes in the universe? Indeed, this is possible because there are multiple black holes in the universe. That's very nice. So, well, yeah, actually black holes are really cool. So we do have, actually I don't know how many black holes we have in the Milky Way, but at least there's one really big black hole in the center of each galaxy. I think each galaxy. At least all of the big ones. And they're usually millions or billions of solar masses. So they're really, really large. And whenever a big star dies, they explode and they leave behind a small-ish black hole, around, well, 1 solar mass or so, or 2, somewhere in this range. Because it's just the mass of the star that falls into a black hole. And there are tons of stars that have died until now, so there are loads of black holes in the universe. Actually, we are thinking about if dark matter could be black holes. So that's a thing called primordial black holes. And we think maybe at the beginning of the universe, black holes were created. And those are the dark matter that we can't see with our telescopes. So dark matter is, well, matter that we can't see with telescopes, and we don't know what it is. and people thought it could be black holes. At the moment, we are quite sure it's not black holes, but we haven't completely excluded it. But yeah, certainly there are quite a few black holes in the universe. Okay, so did I miss any questions? I don't think so. So yeah, then we are also at well, 8 p.m. European time, or whatever is in your time zone, 11 p.m. at 11 a.m. in your time zone.
11 a.m. for me.
Thank you for getting up early.
Thank you. That early.
Thank you all for watching. Thanks you all for sending us those great questions. And if you want to see more, there's a really cool, I think it was called Einstein versus Newton, stream tomorrow on this channel on YouTube. Otherwise, we'll be here again next Monday. So if you want to ask more questions and hear more cool stuff about the universe, join again next Monday, same time, same places. Thank you all. Thank you, Eric, for being here and giving us all these answers. And see you next time.